Hello, everyone, and welcome to the TinyAction challenge. This challenge is focused on low resolution activity recognition. The challenge was organized by CRCV at University of Central Florida, and this is the organizing team. The team was led by Professor Mubarak Shah. We have postdoc Shruti Vyas, and we have PhD students Ayush, Praveen, and Tushar, and myself, Yogesh Rawat, and I'm an assistant professor at CRCV. So the agenda for today's presentation is first I will give you a brief overview about the challenge, and then we will have talks from the top performers. Now let's first try to understand why exactly we need to focus on tiny actions. So tiny actions are actually very common in real world scenarios. For example, if we look into surveillance videos, if we look into security, or if we look into autonomous driving, and there are many other scenarios. So the actual activities captured are they can be a very low resolution, and the reason is they are actually occurring very far away from the camera. So here I'm showing you a sample video from Virat dataset. So this dataset is actually focused on surveillance videos. And here we can observe that the camera is actually placed at a location, and all these activities are happening far away from the camera. So we can see that the actual resolution of these activities is not that high. And specifically, it's very common if we focus on this top region here. There is a person performing some activity which will be very tiny, probably a few pixels. If we compare this with some of the other existing data sets which are focused on activity recognition, such as AVA dataset, so here we can see that if we look at this particular instance, so this activity is like captured very carefully. The camera is totally focusing on the actors, and we are not missing any details here. And of course, this is also very important for some applications, right? Robotics. But if you talk about surveillance security and all these applications, it's not that relevant. Now, first, let's try to understand where the research in activity recognition stands today. So most of the existing research, which is trying to solve the problem of action recognition in videos, it uses high quality videos. So if you look at like the data sets which we have, like UCF 101, we have GHNDB, we have Kinetics, and we have many more. So the videos in all these data sets are actually high resolution. And here I'm showing you some sample video frames from some of these data sets. And you can see that clearly the actor who is performing the action is clearly visible. So there is no issue of like the resolution or missing details or any other grain in the video frames. Now, if we look into TinyActions, so there has been some initial effort, and what has been tried is the videos which we already have in these existing data sets which are high resolution, they can be easily downsampled to low resolution. So we can call that like synthetically downsampling. And the issue is these downsample videos are not realistic. That's not how like the real world low resolution videos will look like. So if you look at the same sample of video frames which I showed you earlier from these data sets, even if we downsample them to a low resolution, of course we have a smaller resolution now, but if we look carefully, the finer details are still there, and we don't have like any grain or any blur which is always present in videos which are actually of low resolution naturally. So that's a big challenge how we get those videos, and that's what we have focused while we create this data set. So we want these video samples which are low resolution to be realistic. And so what we did is we utilize this Virat surveillance data set, and at the same sample which I showed you earlier. So if we carefully look at this, we have these activities which are actually happening far away from the camera. So they are naturally low resolution. So we utilize that fact, and based on this, we created a data set for benchmarking this task. Now, a quick comparison with other data sets when we look into this Virat. So we are trying to compare with these three, AVA, GHMDB, and UCF101. And what I'm showing here is the ratio of the activity region to the complete frame of the video. Right. So if you look at AVA, you can see that the activity region is actually covering 30%. So this 0.3 level here in the y-axis. So 30% of the full frame, and it's similar in GHMDB as well, pretty much close. So in UCF101 again, so these are realistic videos, and we can see that it's a bit challenging here. It's just 15%, but when we look into Virat, it's close to 1%. So which makes this more challenging and more useful for the task of which we are trying to solve here. And so what we did is we have created this benchmark data set, which we call TinyVirat. And these are few properties of this data set which we have created. So these videos are actually realistic low resolution. And the reason is we used Virat, which has naturally occurring tiny actions. And these actions are actually captured in a surveillance environment where the camera is placed at a distance. So these activities are actually happening far away from the camera. So they have like all these properties which we usually have in these real world low resolution videos, like they lack details, they are kind of blurry, which makes this more challenging and realistic. So here is like another sample from Virat data set, and we can see that some activities happening at this region. So if we zoom in to that area, we can see that a person is getting out of a car. And this is like a realistic low resolution video. If you look at this, the finer boundaries and all those fine details are actually missing here. So let me show you some more samples from this TinyVirat data set. So these are sequence of frames for each sample, and you can see that we have all kind of distortions which should be there in realistic low resolution videos. And one interesting thing about TinyVirat is the resolution of the video samples, it's not fixed, which is usually the case with all the other existing datasets which are focusing on action recognition. So we have a wide range, and depending upon like what was the actual resolution when that video was captured, we just preserve that and store that as a sample. So that's one aspect. The other interesting aspect is the video clips are actually, they have multiple labels. So multiple activities can happen at the same time, which makes this even more challenging. In this plot, I'm trying to show like how the resolution varies for the activities which are there in this data set. So on the x-axis, I'm showing the activities, and the y-axis actually shows the number of samples for each activity. So you can see that the distribution is actually varying a lot. So there is some kind of disbalance as well, which is also interesting. And here we have color-coded different bins depending upon the resolution of the video clips. So you can see here that the top one is the resolution which is between 0 cross 0 and 20 cross 20 pixels. So that is coded as blue. And if we look at maybe these three activities here, walking, carrying, and standing, so most of these samples are actually falling in that region, so which means that these activities have samples which are pretty small in terms of resolution. So the second is orange, which is actually between 20 cross 20 pixels to 40 cross 40 pixels. And we can see that most of the activities like which have these orange bar, so they will fall in this category. So the idea is basically we have a lot of variation in terms of resolution, and which is I think a unique property of this data set. Let me share with you some more details about this data set when we compare this with UCF101 HMDB. So from resolution point of view, As we know that these two data sets, the videos are 320 cross 240, so all the videos have fixed resolution, whereas in TinyVirat, the resolution is varying between 10 cross 10 pixels to 128 cross 128 pixels. The third column over here is showing the average number of frames per video. So in this case, we have around 93. So again, it's not fixed. It varies from sample to sample. Some activities are long and some activities are short. And another unique thing is it has multiple labels which differentiate it from these two data sets. In terms of number of classes, we have 26 different classes, and we have roughly around 13,000 samples in this data set. Now, for this challenge, what we did is we extended this data set, and we have a second installment which we call TinyVirat version 2. So these details remains the same. It's just like we have more training data now. We have roughly around 26,000 samples in this extended version of TinyVirat. Now let's talk about evaluation. So since this is a multi-label classification problem, we are using three different metrics. So we have precision, we have recall, and then we have FN score, which is the main metric for ranking different participants. And all these three metrics are computed class-wise. And the evaluation is done on around 6,000 testing samples. Now, before showing you like the performance of the participants, uh, I will show like the baseline scores. So what we did is we took the standard action classification models and trained on this data set. So we used R2 plus 1D, we have Resonant 3D, I3D, and White Resonant. And we can see that they are more or less similar. So R2 plus 1D performs the best among these four. So we have a F1 score of 0.32, a precision of 0.34, and a recall of 3.7. Now let's move on to the performance of the top teams. So rank one is a Deep Blue AI with an FN score of 0.47, precision 0.51, and a recall of 0.49. And then we have in the second place team name Along with an FN score of 0.44, and then we have a team from University of Hong Kong and SES Tech with an FN score of 0.41. So compared to the baselines, which was using R2 plus 1D, they have actually improved a lot. But still, if we compare this with like the existing data sets, which are for activity recognition, there is a lot of scope to improve this performance further. So we are keeping the server open for submissions. So if you're interested in this, please go ahead and try this data set out. So that's all I have regarding the task introduction. Next, we will have presentations from the top performers. Thank you.
Hello everyone. I'll present the solution from Deep Blue AI team for TinyAction challenge. I'm going to share our work from these three aspects: task and data analysis or solution, and the conclusion. First is the task and data analysis. From the annotation field, we can know that this computation is a multi-label action recognition task. There are 26 classes, and we roughly group these categories into 4 parts: activity, vehicle, specialized, and others. The most striking feature of this dataset is the real-world low resolution. The videos in the dataset are realistic and extracted from real-world surveillance videos, which may suffer from green camera sensor noise and other factors. All the videos are captured at 30 fps, around 3 seconds per clip. It contains arbitrary sized low-resolution videos, which ranged from 10 × 10 pixels to 128 × 128 pixels, with an average of 70 × 70 pixels. Next, I will introduce our solution. For the action recognition algorithm, we only tried TSM, TPN, only, and CSN due to lack of time. Among them, CSN, that is channel separated network, show great advantage on the other two. Our best single model result is got from interaction reduced CSN with ResNet 152 as a backbone. Binary cross entropy loss is adopted for the multi-label task. We choose SGD as our optimizer and use warm-up at the start freeze of the training. The config of the learning rate is also listed in the slide. For the augmentation, we first apply a random resize group and then resize to the scale of 128 multiply 128. Another random flip is followed. Experiments show that the scale is a factor that have a great impact on the result. We only tried two scales, 128 and 70. The former has a much better score. In the inference freeze, we use crop as a candle test time augmentation. That is, crop the four corners and the center part of the image with the same given crop size and flip it horizontally. The final result is the average of the 10 crops. We also try other TTA methods like flip and multi-scale but get no improvement. The popular ensemble method, five-fold cross validation, is also adopted, which boosts the score significantly. For the post-processing, we try many different thresholds and choose one which got the highest score. If there is no confidence score about the threshold after sigmoid operation, we just keep the category with the top two scores. As mentioned earlier, we can group the 26 groups categories into four parts. We think it's reasonable. Only one class can be retained at most within the same group, so we just keep the one with the highest score above the threshold within every group. The chart on the right side show how we improve our score step by step. Finally, let's make a conclusion. A powerful action recognition algorithm, a suitable scale, a well-trained model, 10 crop, five-fold cross validation, a suitable threshold, and some tricky post-processing lead to our final not bad result. Thank you.
Hello everyone, I'm Liu Chen. Today I will talk about our work in TinyAction challenge. The speech will consist of three parts: background, proposal method, and our experimental results. In real-world civilizations environments, the actions in videos are captured at a wide range of resolutions and may appear very tidy. Therefore, recognizing such actions becomes challenging at a very low resolution. In this challenge, the focus is on recognizing tidy actions in videos, which makes them realistic and more challenging. Our team analyzed the datasets and found it contains arbitrary sized low-resolution videos, which ranged from 10 pixels to 128 pixels. So we proposed a two-stage method for recognizing TinyActions in videos, which utilizes a video super resolution model to improve the quality of low-resolution actions and then recognize the videos. For video super resolution steps, we use basic VSR model. It presents an information review estimations and a couple progressive scheme to facilitate information aggregation, and lead to a state-of-the-art performance. We first scaled the video with a height of less than 96 to a size of 64, and then used the video super resolution model to expand it to a size of 128, and for other videos to scale it to the size of 128. The second stage, action classification network. We use slow-fast and TinyNet network to train several models. We believe that ensemble the strongest models can get more better results. We also use multi-grid to train our network. Another important thing is that the pre-trained model on KNet 400 can improve the training results. The training stage is conducted on a 8x2080 time GPUs with 12 GB memory for each GPU. The above table shows our experimental results. We fused the prediction scores of all models to get the final results. Our proposed method achieved 0.442 in terms of F1 soccer, ranking second in the TinyAction challenge. Finally, congratulations to all participants and winners, and special thanks to the workshop and challenge organizers. We learned a lot and enjoyed this competition very much. That's all. Thank you for your attention.
Hello everyone, my name is Tian Geng, a master student from University of Electronic Science and Technology of China. I will introduce our solution to TinyAction Challenge 2021. Our team includes Teng Wang, Tian Geng, Jinbao Wang, Feng Zheng, and me. I will introduce our solution to TinyAction Challengers 2021. The presentation is divided into the following parts. Action recognition as a fundamental problem in video-based tasks aims at distinguishing the actions like human interactions, human objects interactions, and so on. Nowadays, it becomes increasingly demanding in video-based applications such as intelligent surveillance, autonomous driving, personal recognition, and entertainment. However, the most existing action recognition datasets mainly consist of high-quality videos, which are distinctly visible with high resolution, and there are few datasets that are realistic and collected from real-world complex environment. In detail, TinyVariate V2 dataset is a multi-label dataset with multiple actions per video clip, and particularly the videos in the dataset are collected from real-world surveillance videos with naturally low resolution. In the TinyVariate V2 dataset, there are a total of around 26,000 videos with above 17,000 trained videos and 6.1 thousand testing videos. The average length of the activity is around 3 seconds. The distribution of the video duration is shown below. Besides, the resolutions of videos in the dataset are ranging from 10 to 128, but we found that the most of the video's resolution in the dataset is 112 times 112, as shown in the bottom left figure. And in the pictures, we can see the videos are very blurry and have usually multiple labels in one clip. By analyzing the data, we aim to address two main difficulties. The first one is caused by low resolution. From the pictures, we can see that the left picture contains a lot of information, while the right image with low resolution loses a lot of detail when zoomed in. Besides, another issue is multiple labels that will require a more efficient model to classify them. Here, we will introduce our framework for this task. Firstly, given videos, we sample 16 frames from each video, and as mentioned before, we found that even though there are various resolutions of videos in the dataset, the large proportion of videos have the resolution of 112 times 112. So, in order to extract better video spatial temporal features and better adapt to the model, we then recess all frames into the same size of 112 times 112. Secondly, R2+1D is used as our backbone network to extract the spatial temporal features of actions, which was pre-trained by large-scale video dataset to obtain better initial weights for the following fine-tuning. After feature extraction, we apply asymmetric loss for multi-label action classification. We will introduce the components of our method clearly in the following slides. Here, we will introduce our backbone model first. Specifically, we utilize R2+1D with ResNet 634 as our backbone network to extract the video features, and in order to obtain better parameters, we initialize the model with pre-trained weights on the IG16 milling and kinetics datasets. Note that the pre-training process is based on the relatively low resolution inputs, which can alleviate the potential distribution gap between the pre-trained datasets and the target datasets. R2+1D is built on 2D ResNet. It ends the 1D temporal convolution into every 2D convolution block. And compared with 3D ResNet, it factorizes the 3D convolution into separate 2D spatial and 1D temporal components, very significantly gains in performance. And there are two advantages of R2+1D backbones compared with 3D counterparts. Firstly, despite not changing the number of parameters, R2+1D doubles the number of nonlinearities in the network due to the additional ReLU between the 2D and 1D convolution in each block of ResNet. Increasing the number of nonlinearities can increase the complexity of functions, which is beneficial for the feature extraction. And the second benefit is that forcing the 3D convolution into separate spatial and temporal components renders optimization easier. As shown in the figure, we can see that for the same number of layers, a 2 plus 1D yields not only lower testing error but also lower training error compared to a 3D. It indicates that optimization becomes easier when spatial temporal filters are factorized. And the gap in the training losses is particularly large for the nights having 34 layers, which suggests that facilitation in optimization increases as the depth becomes larger. Since in the typical multiple label setting, a video contains on average few positive labels and many negative ones, this positive-negative imbalance dominates the optimization process and hurts the representation ability of the model. In this task, we apply asymmetric loss ASL to address the inherent imbalanced nature of multi-label datasets. Here, we compare binary cross-entropy loss with asymmetric loss. As commonly done in multi-label classification, given key labels, the base network outputs one logit per label, zk. Each logit is independently activated by a sigmoid function, and yk denotes the ground truth for class K. So the total classification loss is obtained by aggregating a binary loss from K labels. So a general form of a binary loss per label L is given by this, where Y is the ground truth label and L plus and L minus are positive and negative loss parts respectively. By contrast, as for the asymmetric loss, the two mechanisms of asymmetric focusing and plausibility shifting are integrated into a unified formula, where P is the network's output probability. ASL allows us to apply two types of asymmetry for reducing the contribution of easy negative samples to the loss function. Soft thresholding via the focusing parameters gamma minus and gamma plus, and hard thresholding via the probability margin M. Here, the experimentation details and the experimental results are shown as follows. During training, for each video clip, we sample 16 frames randomly and then we set the frames with various resolutions to the same size, 112, and then feed them to network R2 plus 1D. During evaluation, we sample 16 frames randomly 5 times, and then average the classification scores to get the final results. From the table, we can see that when using 5 samples, we can get better F1 score and recall result. In conclusion, we use pre-treat R2 plus 1D for feature representation and an classifier with an asymmetric loss to address the positive-negative imbalance problem in multi-label classification datasets. Finally, We assemble the prediction scores of 5 clips to boost the final performance. That's all. Thank you for your listening.